Nashid Alam. I am currently a lecturer in artificial intelligence and working at the Department of Computing and Mathematics at Manchester Metropolitan University. As you can see in my front slides, I work on medical image analysis specifically. So for that, I also collaborate with other universities as well. So I also have an honorary lectureship position at Aberystwyth University in Wales in the UK. So today we will be talking about my research, what I'm doing here, and also what we are doing in the department as well. So some of the research that you will be looking at, it's what is my own research and some of the research that my students are doing in our lab as well. And in general, what we are doing department-wise. So what are the cool stuff happening in our university. So starting with the agenda, so I will be mainly focusing on medical image analysis, specifically mammography, and a specific kind of abnormalities that's related to breast cancer detection and diagnosis. But then I will be highlighting to some of my students well. So you'll see what are the other domains that I and my students in my lab are working. And what are the current research that we are doing in MMU? We have quite a diverse group, and it's quite a big group. We are part of the human-centered computing group. So people are working with games development, cybersecurity as well, computer vision, advanced machine learning for image analysis in general. And then at the end of it, I will give you some time. We'll have some time for open discussion, and we will see if we can navigate some sort of like collaboration opportunities. So let's get this started. So like I said, we're talking about machine learning, advanced machine learning, or deep learning, if you may say. Machine learning in healthcare system. In terms of detection and diagnosis, so we talk about breast cancer. And in general, when you talk about cancer, there are two different challenges that we normally face, specifically in clinical settings. The clinicians face this. One is late diagnosis, when the cancer is in advanced stage, and it's quite late, so that treatment planning can get a bit tricky. And the thing is misdiagnosis, where when you have false positive and false negative, so the clinician may say, all right, you have a normal screening, but the student will, the patient will come again at a later date and saying they have some symptoms, they do the screening again, and it happens to be turned out like, oh, it's a misdiagnosis cases. So late diagnosis and misdiagnosis, and how we can actually fight these two problems, how we can actually avoid late diagnosis, and how we can think about in the national healthcare system, how we can assign resources carefully and in an optimal way. So here you can see the abnormality we're looking at. The image we're looking at is an X-ray. So in the right bottom, you can see in mammogram, which is a two-dimensional X-ray of a breast. And when it comes to cancer, there can be different kinds of abnormalities that can help the clinicians to identify cancer at an early stage. But when we talk about the early stage cancer diagnosis, microcalcification cluster is one kind of abnormalities that are most dominant and dominantly be seen in those clinical images, because you can see in the top in the top right there are calcium deposits, very, very small, type 2 or 4 pixels, and this is scattered throughout the mammary gland. And these are the only kind of abnormalities that is visible in the mammogram that can be used as a very early signs of cancer. There are other kind of tissue abnormalities as well. There are masks, there are mammographic asymmetry, but because microcalcifications are very small, it can be hidden within the cancerous, within the normal tissue. It's quite challenging. And if you can find it through a system that can actually point out the clinician, all right, we might have figured out some sort of like early sign, or maybe they can actually prompt the clinician. Maybe the patient might need further analysis. They may be referred to a biopsy, or if it is a normal microcalcification, then the patient can have regular screening in 2 years' time. That's what happens in the UK. So here, if I can show the audience these two images. So both of these images contained microcalcification cluster. So there's a right image and a left image. So if I ask you, to the audience, can you tell me which one is the cancerous one or which one is the non-cancerous one? So do you think the right one or the left one is either cancerous or non-cancerous? So do you have an opinion to this? Maybe Zobia can help me understand what is the audience poll.
Yes, audience can write either in the chat box, or you can speak because the speaker wants to have a discussion, to have a presentation in interactive mode. So the audience can write in the chat box that which one they think is the cancerous and which one is the normal.
Yeah, so maybe I'll give them like 30 minutes, and then Zobia can actually tell me what is the poll. We are getting audience.
No, but because in the chat, we can see in the chat, Nashid, because Javeria is saying that maybe it's the left one that is cancerous.
All right. So majority is saying the left one. So let's see if it is the left one or not. So we can see.
And Amjad is saying it's the right one. All others are saying left one.
So who is correct then?
Yes.
Amjad? Maybe. So the right one in my screen is the malignant one, and the left one is actually benign one. So you can see there is lots of, there can be a debate because the texture, the distribution, if you look using your human perception, can be sometimes misguiding. Some people might say it benign, some people might say it malignant. And what happens in the clinical settings when the clinician sees lots of this kind of images, their eyes can get tired. So they are more prone to make this kind of mistakes. So this is where we need this computer-aided diagnosis system, where those systems can actually flag, localize, and give them a second opinion. So these are not the standalone system that we're trying to develop. These are the system to assist, to help the clinicians to identify and diagnose the problem, so that we can actually avoid unnecessary biopsy or misdiagnosis. So this is a challenging problem. So before I dive into the technical part, I just want you to understand what was the clinical need, what was the drive to conduct this research, why clinicians are interested to work with us. So this is quite a challenging problem, because you can see from the abnormalities, this can sometimes actually blend very nicely with the background tissue as well, like you can see in the malignant cases. Sometimes it can be hidden, bits and pieces can be hidden in the normal breast tissue, and which can be challenging sometimes to pick up. And here is a collaborating clinician who is based in Norwich. And this is how in the UK we do the screening. And those clinicians use these systems, where you can see the clinicians is sitting in a dark room and trying to interpret the mammograms. And like I said, in the NHS, clinicians are mostly overwhelmed. They get overwhelmed a lot with lots of images. So this is what we are trying to help them. And those clinicians actually help us. So this particular clinician that you can see in the screen, he works with us in terms of providing data annotation and in terms of validating our computer-aided system. And another thing when we talk with the clinicians is like we have intra-observer and intra-observer differences as well. And when we have less clinicians, can we have this kind of CAT system to help them to combat those kind of problem? And of course, with those assistants, how we can actually avoid unnecessary biopsy, because biopsies are expensive. It costs the government, it costs the hospital, and of course, it costs panic and anxiety. And the biopsy process causes physical discomfort as well, because you need to press the needle inside the body to get the tissue out, to do some sort of histopathology analysis. So how we can actually avoid those biopsy. And according to the current statistics, 80% of the biopsy is unnecessary. So if you can avoid this unnecessary biopsy, you are actually helping those national healthcare system hospitals around the UK in terms of cost management as well. So this is why we need those computer-aided detection and diagnosis system, which is not a standalone system, but it can be worked as a second reader. It can work with the radiologist hand in hand in terms of assisting them. And there are some sort of related work. You may actually ask, why is the need? Because there might be lots of literature that you can find who are working on the same kind of problem, who are trying to solve the same problem. But the problem is, when it comes to clinical deployment, none of the existing methods, it gives full satisfaction to the clinicians, or it gives clinically acceptable results. Sometimes some of the paper actually report like we have highest accuracy, they compare their results with other state-of-the-art method, but then you show it to the clinicians and they just disregard it. Because for them, clinically, it's not, first of all, meaningful. You're giving them some numbers, but they want the clinical interpretation. So interpretability is one of the things that we also look at in our lab as well, specifically when we work with deep neural network or deep learning. We also work with conventional machine learning system as well, and sometimes we try to integrate those conventional handcrafted features with the deep neural network features, because it also brings some sort of like explainability part to the system. So we are trying to create a fast, reliable, and cost-effective CAT system that can actually assist the clinicians, avoid unnecessary biopsy, so that the patient will have better chance in terms of getting successful treatment. So the result I'm going to present here, for the first one, it's pretty much on a small size of data set. So it is interesting because in these days for advanced machine learning, you need lots of data, thousands and thousands of data, but you can see we are trying to get a working system that can be trained on less data. So here are 3 data sets. 2 is digitized, and 1 is the digital one. The bottom one is the digital one. And the annotation you get in this data set, the ground truth, is something like this. So this annotation is done by clinicians, and it is actually validated against the pathology data. So this annotation is biopsy proven. So it maintains the gold standards when we are getting those annotation. So we use this annotation to crop a region of interest that contains microcalcification cluster. You can see the tiny bits of, dots, which is the calcium deposit scattered throughout the mammary gland. And this is our region of interest. And then we use this patch image for our deep neural network for segmentation or classification purposes, or for progression purposes as well, and prediction purposes as well. So this is a segmentation work that appeared in a conference paper in 2018. So if we focus on how it worked with this, we have the mammogram with annotation, we do the path extraction, and then we enhance.
Excuse me, Nashid, I think your screen is not visible.
My screen is not visible?
Yes, if I'm not wrong.
Okay.
Maybe it stopped sharing now, maybe.
You're not allowed to share your screen. You can ask the meeting host to turn on screen sharing. That's what it says.
Yes, maybe some of the hosts maybe turn off the screen sharing option. So please allow it now.
Entire screen. Share. Can you see it now? Zobia?
Yes, it's okay now, Nashid. It's okay. Thank you so much.
Yep. So I was here, I guess. Is that where it stopped sharing?
Yes, exactly.
All right, good. So I was just talking about how we have done the segmentation from the annotation. So what was the process that we have followed? So we have this memo, and in the red you can see the annotation, and with the help of that annotation we have done some sort of patch extraction, we did some image enhancement, and from this enhanced image we use some sort of bicubic interpolation technique, and then from the enhanced image and interpolated image we actually created a different image, which is pretty much like subscripting it. That's why it looks very, very dark. And then for better visualization, we do the double precision conversion with a specific intensity range that you can see here, 0.0 to 0.9. And then we have performed a series of morphological analysis where we actually played with the intensity, and then we remove single pixel, because in terms of clinical definition, single pixel cannot represent a microcalcification. And then we have done some erosion and dilation operation, and then we again keep half of the intensity, which falls into the highest half ranges, because if you see microcalcifications here, these are pretty much like very small but bright pixels. So that's why we are dealing with the high intensity pixels. So we have two phases. So this is phase 1, where we have generated image A, and in phase B, from the enhanced image, we pass it into a filter. We got the filtered image. We then keep the 5% of highest intensity values within the image, and we have got image B. So in phase 1, we have got image A. In phase 2, we have got image B, and both of the images got integrated to get those images together to create image C. So from this image C, we have calculated connected component here. For that, we have used 8 connected component, and we have performed some morphological analysis here, an erosion operation, and you can see it looks pretty much very similar to the microcalcification we have previously seen in the annotation patches before. And then what we have done, we have this erosion image has been divided into 100 by 100 pixels. So these are the semi blocks inside the patch image. And because I have told you the microcalcification cluster cannot contain one single pixel, so we identify the single pixel here, and then we remove the single pixel. So finally, we have got the segmented images like this. So in the right side, you can see how it looks, very tiny microcalcification cluster. It looks quite big here because you are maybe looking at in a projection screen, and I'm sharing a full screen, but it's really, really small when it's embedded in a mammogram. So in the yellow color here, this is the annotation that we're getting from the clinicians, because it's very hard to get the delicate line around each individual foci. So we get a cluster rather than having an individual microcalcification. In fact, in the clinical definition, microcalcification individually doesn't contain any necessary significant information, but when you think it as a cluster, as a whole cluster, it gives you an overall idea whether it's cancerous or non-cancerous. So the clinicians actually annotate it as a cluster. And here you can see our images. So we overlap the boundary, this yellow boundary here on our segmented image, and we can see it's pretty much lots of our bits and pieces that we have picked up from our techniques actually quite aligned with the bits and pieces that falls within the annotation provided by the clinicians. So you can see there are some sort of like conventional machine learning techniques. I think it's image processing techniques, not the machine learning one, but it works very, very well. And then step by step, you can actually explain it to the clinicians what you have done rather than using a black box or a gray box. So there are some other examples you can see here from different patients where we have actually created some microcalcification cluster segmentation. So sometimes we have actually some extra bits and pieces, but in general, if you see the results, those results are quite promising. I will show you some of the mathematical matrix, numeric matrix, where we have quantified our results. So we have calculated DICE matrix, so Dice coefficient. So where we get the radiologist annotation, from the annotation we created a reference mask, we extract the border, and then we overlay the border on the segmentation, and then we created a convex hull based on the boundary that we have got, and then from the convex hull we created a mask, and then we'll overlay the reference mask on the convex hull to calculate the DIAS. So this is our DIAS score. And we also compare the DIAS score with other models. So Arnaud's Oliver, he actually have some sort of segmentation techniques here, which has an overall DIAS, which is pretty low compared to our results as well. There is another technical area rank based segmentation, which is also very low. So this is on DDSM and this is on MIAS databases as well. So we can pretty much see our segmentation result. It's promising compared to some other, techniques that use conventional machine learning. And then, of course, because we have the segmentation results, we wanted to move on to look at how the classification will work for this method. So we extracted from the segmented image, we extracted 51 features. So you can see some of the features here. So these are mathematically calculated. So area, some geometric features, some texture features like background intensity, that sort of thing, because tissue texture is very, very important. But then the important thing is when you extract these features, these are the numerics. So we need to give them some clinical meaning as well. So this 51 features, numeric features, were aligned to radiological characteristics, and this was verified by a radiologist. So we show the features and we ask the radiologist, can you actually map these features? Can we actually see that these features are in line with the radiological characteristics? So it's quite explainable, that the features are quite explainable, and it has some clinical groundings. So which is a good thing in terms of explainability. And then the three technical output that I have shown before for the DIAS, we have used segmentation images from these three methods, and then we extract those 51 features, and then we do the union of important features. So 51 features was a lot of features, so we do some sort of like majority voting stuff, and there's some other machine learning algorithm that we have used to extract those important features. So that can be another separate talk, because you can see we have published paper based on this slide actually. When we use this union of features from the 51 features, we ended up 15 features here, and ultimately we use these 15 features for our ensemble classifier. And we did some majority voting with these 15 features. We'll also have, you can see the clinical characteristics that we have mapped here with the statistical features. And then from our segmentation approach, the image we have generated, it gets an accuracy around 94%, where we compare it with other images generated from other methods using the same database. Our approach got pretty much high accuracy and the area under the curve score. So this is also another paper as well. So you can look at that paper. It was published in Dicta 2018. So if you want to need to get more understanding and insight about it, just refer to the paper. So we're talking about the classification, and we only have seen some of the features, which are like some statistical features, size, shape, and texture. So when we take it to the clinicians told us the most important features is the distribution, because when they interpret these images, they actually look at the distribution of this microcalcification. So remember at the beginning I told you, when those microcalcification are single dot or a single object, it is very unlikely that it carries some significant clinical meaning. It has some meaning, but it might not be significant. But if you need to have a significant meaning of that whole object, you need to think it as a cluster. And when you think it as a cluster, you need to think about as the distribution, how those clusters are distributed. Yeah. So what we have done, we segment the image and then we numbered every different cluster. And then we do some dilation. When we did the dilation, we use a structuring element and we scale it to the scale of 6. So because we tried other scalings, but 6 give us a nice subcluster, which was created from the segmented images. So I'll show you how it works. So when we dilated it, we see some of the blobs get actually merged together. So here at the top, you can see there are 3 blobs, 8, 10, and 5. I think it's 7 or something, 6. So you see 3 of the blobs got actually merged when we scale it for dilation. Also this got merged with this 4, 8, and 5. So all of this blobs got merged together. That's what you can see. And this is what we have done. So we actually track the merge blob after dilation to create intercluster that you can see here within the yellow circle as well. So after we do the scaling, we merge it so that we can create some intracluster. So a cluster inside the cluster, and we try to find out what are the intercluster and intracluster relationship. And this is where we have actually separate all the intracluster. So you can see there are 7 different cluster. We visualize it separately in 7 images as well. And then we try to get an understanding how these clusters are actually interrelated to each other. So we created an edge, the distance, so the centroid from one cluster to another cluster. So edge among the subcluster, that's what we were focusing on. So we think about the intercluster and also the intracluster based on the dilation that we have done, and we considered the number of edges among different subcluster. And then we also think about, so that was a feature here that we have used, and another feature was the linked list based centroid mapping. So when we have dilated, the centroid get merged together. So we name it as sync node. So you can see here, one centroid is called candidates, source node, and we also have a sync node. And based on the distance, we have actually created connection in between those source and the sync node. So for an example, here you see the images, and you see the distance table, and you see the linked list generated from here. So here it says the candidate source node was number 3. So if you think about number 3, it was synced with number 6. So this is number 3, it was synced with number 6, and then number 6 was synced with number 11. So number 6 was synced with number 11, and this is actually skill 4. So you can see here, number 3, number 6, and so number 3, number 6, number 6, number 11. So there is one missing, but I think it's a typo, but there will be number 11. So if we think about this one, 4, 8, and 5, so 4 sync with 8, 8 sync with 5, and there is no other 5 here. If you go back to the 5 here, 5 syncs with 8, where we already have 8 linked with 4. Or if we go to the 7, so 7 with 9, so 7 with 9, 9 with 7, you go to the 10, and then you see it's linked with 9, which we have already visited and which is already in the linked list. So this is how the linked list work, and we have used this as a features as well, which gives us around like 98% accuracy. So intercluster and intracluster, this is something that we also look at. So distribution, that's something that we look at that give us around 98% accuracy. But then we thought about, all right, so why don't we look at some graph topological method and see, because when we look at this mammogram, those mammograms are X-ray, which is 2-dimensional X-ray. So we were thinking, all right, from this 2-dimensional mammography, can we get some 3-dimensional information? And how come this can help us in terms of, computer-aided diagnosis to detect this microcalcification? So we use this same segmented image, and from this segmented image, we created a multi-scale graph topology here. So we dilated the microcalcification in different scales. And once we dilate it, when they get dilated to each other, we created a edge here. So we dilate in different scale, it get merged, and we have created an edge. So when we create it for multi-scale, the more scale increase, the more edges we are having here. So this is my multi-scale graph topological model from this sample image that you can see in the top. And then what we have done here, we have extract those graph topological features. So this is the number of edges connected to one another. All right. And then we also have, on the other hand, the statistical and morphological features that I have previously showed you, which was 51 different features. And then we merge those statistical and morphological features with the graph topology features. So this graph topological features is actually the three-dimensional information that we are trying to extract from a two-dimensional image. So that's why it's multi-scale graph topology. And then we try to select significant scales and significant features to classify benign and malignant cases. So this is what I was trying to explain. You dilate this in different scale. The more the dilation happen, you can see the more edges you're getting. So the more scale you're increasing here. So here you can see the more edges you are actually getting among the microcalcification cluster. So it gives you an idea about of the connectivity and the distribution about of the microcalcification, and you have got a 3D idea, like a tomosynthesis data, like a 3D X-ray kind of information where you get slice by slice information. But here, because it's 2D, you don't have different slides, only one slide, which represents the 3D objects, but you're trying to get an idea, all right, how can I get this 3D topological information from here? So this is how it looks actually when we implemented. So the experiment, we're increasing the scale, and you can see with each increasement, we are getting more and more edged here. So this is a malignant case. So you can see the malignant cases are quite densely connected. That's why we're getting lots of edges, all right? So here, if we compare the benign and malignant cases with the same scale, you will see how the connectivity actually are different among benign, which is a non-cancerous case here, and the malignant, which is the cancerous one. And you can see over different dilation, when we increase the scale, the malignant one is more densely connected to each other. So it looks very clumsy because it's more edge, it's more densely connected, all right? And we use this as a feature. So how the distribution happens, how the edge are connected, how densely they're connected to one another. Because we can see there is some useful information, and this was also validated by the clinician, like the distribution is very, very important stuff. So you can see here, for the same scales, for an example, scale 12, you see benign one is less densely connected, where the malignant one was more densely connected. Same for scale 26 and scale 45. You can see lots of edges for the cancerous one, but for the non-cancerous one, it's not much of the edge that you can see here. So these are the graph topological features, the equation that you can actually use, and some of the conventional features that we were trying to integrate with the graph topological features. And we wanted to visualize the feature space here. So when we distribute the feature space, we can see benign and malignant one nicely separated from one another, which is actually in line with what the clinician told us. Like the graph topological features actually give them a good information, a good reference point in terms of diagnosis, benign and malignant cases. And when we run this experiment, we actually validate this. Like what the clinician says, it actually aligns with their experiment. And then when we see this is also another paper appeared in 2018. But here, when you see the statistical and morphological features, it's not nicely aligned. And when I will be showing you the result analysis in the later slides, you will see the classification accuracy is quite below when we use the statistical and morphological features. In fact, when we use statistical and morphological features integrated with graph topological features, the accuracy is going very, very down. But when you use graph topological features alone with feature selection, it's quite high. So this is the classifier. We keep the same classifier using the majority voting. Here you can see the graph topological features. We have done some sort of feature selections, and it gives us more than 98% accuracy for 3 of the databases we have used. But when we use morphological features, the accuracy drops drastically from 98 to 75 or 90, in fact, with the feature selections as well. But then we use topological features, but then we decided, all right, we wouldn't be doing the feature selection. So this is one of the collaborators from Chili Chan. She tried to do it without feature selection, but then the accuracy was also quite low compared to what we have achieved here with the feature selection, with the topology features we have got. So I need to make it clear, like this topological features and this topological features are the similar features, but we have done the feature selections as well. And then we integrate the topological features and statistical features together, but this time we have done the feature selection without our images, and it's quite slightly low. So the best we can have is this one, where we have done some feature selection for the topological features, which gives us around 98% accuracy. So we're talking mostly conventional machine learning so far, which is important because these days we can see lots of deep neural network paper got published, and we sometimes ask ourselves, but it's not explainable. But there are some information, because deep neural networks are not completely black box. It is getting gray box day by day. And there are some explainable method also that you can actually integrate with the deep neural network. So I wouldn't actually go to all my works that I have done. I've just cherry picked some of them. So here is another. So for conventional machine learning, you can see the accuracy we have got around like 98% or something for the topological features, which is quite promising. But we wanted to see, all right, let's try some deep neural network, kind of like a vanilla deep neural network. So you can see the vanilla deep neural network we have created from scratch. We have used a global average pooling at the end, and then the fully connected layer for the binary classification. And because this is a vanilla network, so the architecture is very simple. So we were trying to see how the simple model actually works for our classification problem, to classify those benign and malignant cases. And then, because we were working with a very small data set, so we have done some data augmentation and try to extract those feature map. We have shown this feature map to the clinicians. They were quite not happy. It gives a good results though, but those feature maps actually was not clinically meaningful. That's what the clinicians told us. But for the investigation purpose, we keep trying to see how the model actually works. A vanilla model works, which is not very deep, which has a limited data, which is a digital data set. We have around 1,000 data sets, and we've split the data as this distribution, like you have said. And these are the parameter tuning, and we get around 92% accuracy. So though we are using those deep neural network, this is a vanilla one, quite a basic one, but it gives us less accuracy in compared to what we have got from our graph topological features, which were extracted by conventional machine learning. So this is the confusion matrix for the test cases, and this is how the loss and valuation curves looks like. So just to see, it converges very well, the loss curve for training and validation cases, around 50 epoch, and the generalization gap is quite small here. So we are getting quite high accuracy, but still it's not beating what we have got from the conventional machine learning here. We end up around 94% accuracy. And then when we have other networks available to us, it's the highest that we can actually get from our model using tenfold cross-validation. So we're trying to get an idea how the deep neural network can actually work if we use a very simple network, and how can actually it perform compared to the handcrafted features, and if that features are clinically meaningful or not. So what we have done, we integrated class activation map to our network. So we can show this to the clinicians and tell them, all right, this is where the machine, the network is actually looking at when they have done the prediction. Does it make any sense? Is this where you actually look at when you make those predictions? So this is how we actually modified our model to integrate class activation map. So we provided the class activation map with the probability score as well. And which also, like I said, the clinicians actually like the class activation map output, but then when you show the intermediate features, sometimes with some of the features they agree, but sometimes they disagree, and they think in some features they don't have clinical meaningful thing as well. So this is also something we are still investigating, how we can actually make those AI system more transparent, more explainable, so it can be deployed in the clinical settings, and we get this regulatory approval to deploy it. So far, we have seen the work on 2D mammogram, so 2D X-ray. But in our lab, we also do 3D modeling. So we use 3D X-rays as well. So for breast X-ray, we call it digital breast tomosynthesis. And how digital breast tomosynthesis look like? It pretty much looks like the MRI, but it's for the breast. Yeah, it's tomosynthesis data. And we have a private data, which is very, very small, only 2 benign and 3 malignant cases. So what we have done, we have used the annotation from the clinicians. We have collaboration with the University of Pennsylvania. So this data is coming from University of Pennsylvania and the clinicians who are based in the States. So this annotation is from the collaborating clinicians from there. And then from the annotation, we create a mask, and then we do it for different slices because it's a 3D data. And from different slices, we have different annotation. From that annotation, we created different patch images based on the patch images. Using the annotation, we overlaid the annotation to see where the abnormality resides. So I highlighted the abnormality with the green color as well. So these are all the bad guys. These are the microcalcifications sitting here. So we created a heap map. So all the microcalcification in different slices were overlaid, and you can see the higher color here. It represents the more frequently microcalcification occurs on that particular place, all right, because it's coming slice by slice. So around the similar place, more microcalcification actually is created. And of course, then we created a binary image because microcalcification is very, very small, a calcium deposit. So I highlighted it with the green color, so it's more visible. But of course, for analysis, we remove this. And considering all those annotated outline, we created a point cloud because we are dealing with 3D modeling. We're trying to model 3D objects of this microcalcification cluster. So it's a synthetic object that we're trying to find out. And we're trying to see if this 3D object is quite realistic and can be used to train this model so that we can classify benign and malignant cases. So this is what you can actually see here. In the left side, you can see this is the 3D mammogram. So this is actually a video. So you can see here different slides. The slides is changing on the right breast. And in different slides, you can see different abnormalities. Maybe it's more visible with the annotation, but it's normally here and here. So these are the tomosynthesis cases. So what we have done, you can see the point cloud. We have actually used a spline fitting algorithm. We use implicit B-spline fitting algorithm to see how we can actually model the abnormalities in this point cloud. So when we do that, because microcalcification are very, very small, I actually number it. So 15 for an example, 16. So 16 is the microcalcification cluster number, and then you have the slide number 1 or 2, and then you have individual microcalcification number 1, 2, 3, 4. That's why you have comma separated 3 values here. And because it's very, very small here in the 3D space, I actually zoom it and take some screenshot so you can see how it actually looks like. And actually, when you see the biopsy samples, it is quite similar to the biopsy sample that we can see. Yeah. So because it's more smile fitting looks like it, but the morphology is very similar to what we actually see when we get the biopsy samples. So when you take the tissue samples and see those individual microcalcifications, it looks very much like my 3D model that you can see here, that we have generated from implicit spline fitting. And then based on the annotation, we have numbered it, and then we use it as a reference point to localize our microcalcification cluster. And then based on that, we actually place all the microcalcification here in a 3D space, right? So this is actually a pseudo or virtual object that we have created. And we wanted to see if the features that we have extracted from this 3D model, does it have any clinical interpretation? So we send it to the clinicians. The clinician actually have a clinical interpretation mapped with the features that we have extracted from those 3D model here. Yeah, so it has some clinical meanings. And then we extract the feature, we put it in a visual space. It's quite nicely separable, you can see here. So there are 6 different example features I have visualized, but I can do it for all the feature spaces, which was very, very, very assuring. And this is the results that we have got. We have got around 80% classification accuracy with leave-on-out cross-validation. So if anybody wants to work with or collaborate with us, this is something that we are looking at the moment. So deep learning-based segmentation technique, can we have, inter-observer and inter-observer variation investigation when we use this kind of model? Can we integrate features from right and left view, CCML view as well? And can we use 3D modeling, 3D surface reconstruction technique as well? And then we also have collaborators based in the UK, in the States. I'm based in Manchester, so I forgot to include the Manchester Hospital here, but we have nice hospitals. Christie, we are working with Christie, we are working with Manchester MRI, and we have nice computing power from Aberystwyth University, where we use supercomputer wells, and we also have some supercomputing power in our department as well. So there are support and ongoing collaboration happening, but if you are interested to collaborate with us, feel free to drop me a message. And we're talking about breast cancer, but in my lab, some of my students work on other image analysis techniques. So this is something related to hand gesture recognition. It's already published in the journal. This is another medical problem that we are looking at, which is sclera detection system for human identification. So sclera is actually a vein pattern, blood vein pattern, which is very, very important for discover different medical conditions like jaundice, because when you have a jaundice, there's a change in the sclera. Sclera segmentation is also important if you're working on eye tracking system or gaze estimation system. You can use this thing for biometric identification. Also, it can be used in one of the improved image analysis technique, where separating sclera from the surrounding structure like iris, eyelids, eyelashes, skins. It reduces the background noises as well. And sclera detection technique can also be used for surgical planning and ophthalmology to help with the surgical procedure as well. So we also look at other domains, other medical image domain as well, and other medical image processing problem. We also work on brain tumor identification to identify brain hemorrhage. So you can see here how we have one of my students work on segmenting a tumor in brain MRI images as well. And we also work on other image analyzing technique using deep learning stuff. So here we have used graph attention network for facial expression recognition. So what we have done here, we have done adversarial domain alignment for robust cross-domain facial expression recognition. And we have used here classified here 7 different emotion from 6 different data sets. And you can see our model architecture here. This is the pipeline for our GET ADF framework. And you can see the main contribution that we have actually proposed here for domain adaptation techniques. So this is this is a paper published from one of my student. So this is the link that I have put. So it's quite a recent paper published in last December. And so you can actually feel free to go and read the paper. It's quite a good one. I think it's a domain adaptation for facial expression recognition, but I think it can be used for medical image processing. So currently we are thinking about using it, whether we can use mammography data and histopathology data and use this cross-domain, adaptation technique for mammography image analysis as well. The accuracy is quite good. It's quite a promising one. So yeah, she did a very good work. This student is still working on facial express analysis. Another problem that we work on is skin lesion classification. So it's related to skin cancer detection. So we use ISIC dataset. So this is from another student. It was also published on this year actually. And and this is the model, which is where we have include an explainable technique, which is sharp features. So it's actually a sharp enhanced CNN. That method contains 2 different stages where explainable features extraction and those sharp neural network have been trained. And we computed a global sharp value by using a subset of the training set as the background data. And then we calculate the sharp value on the remaining training images for our explainable features. And afterwards, in the training stage of the network, we incorporate these explainable features into the model and develop this, sharp enhanced CNN to improve model performance. And then we try to provide some explainability as well. So yeah, feel free to look at that paper as well. So for this work, we bit other networks that are available in terms of F1 score and ROC curve, but the other matrices, we still need to work on that. So the student is still investigating. It's a PhD student, so he's still working on that. But yeah, it's give us some promising results as well and some good direction for future research as well. So these are some of the highlights from what's going on in our lab. But in general, our department is quite vast. So there are other cool stuff happening in our department. So we're Department of Computing and Maths. We work in 4 different themes. One is the data science, machine intelligence, data and ethics. So if you're working in AI ethics or machine learning ethics, we have some good advocate, some nice professors, quite well known in the research domain working here. And this is where I'm based in, human-centric computing group. So these all 4 are based in the AI cluster. And then we have cybersecurity cluster as well. So if anybody wants to work on cybersecurity, feel free to approach me. I can actually direct you to my colleague and they can actually talk about their work, the cool stuff that's happening for the cybersecurity. And then because we are integrated with the mathematics department, so there are mathematical modeling cluster, they work with fluid dynamics as well for the in terms of mathematical modeling. So we have another group. So these are the 3 themes and these are the sub-themes that we have. And in Manchester, we have AI Foundry, and Cyber Foundry, and there is a Center for Digital Innovation. Our university is part of it. So we work together with other universities because in Greater Manchester, we have 4 different universities. So everyone is working very closely together when it comes to research. And we are also a member of the Tuning University Network, which is good. And if you don't know, we are quite an old university. So we are more than 200 years old university, established in 1824 as a Manchester Mechanics Institute, founded, and over the time it goes through some sort of like reformation. And then in 2024, 2 years back, we celebrated our 200 years. So it's a quite old university as well, with good research and teaching facilities. So if you are ever in Manchester, you'll find us here. So this is our department, and you can see the nice Manchester skyscrapers here. And you can see an Oxford Road here. So on the right side here, it's University of Manchester. On the left side, this is Manchester Metropolitan University. And this road is called the Oxford Corridor. And we think it as a nice, we call it as a corridor because we think this is where the ideas and innovations are happening with both the university. We also have Manchester MRI, where we work with lots of clinicians who actually help us to validate this this AI model as well. So if you go further down to the right side, you'll see MRI, Manchester Royal MRI. And this is the library transformation project, which will be completed in 2028. I need to do some sort of like publicity here or PI talk. So if you ever come in Manchester by 2028, you might see our nice library building here. And yes, this is, I think I need to wrap up now. So thank you all for listening to me, and I'm open to any questions, any discussion, and any collaboration opportunities. This is my email ID. Feel free to, send me an email if you have a cool idea, or if you want to work with me or with my colleagues, because I think you kind of have an idea about how we actually work together. And this is my research activities and how I actually work with industries as well, because we also have some industry partners working with us. So yeah, that's it. Any question?
Thank you so much, Dr. Nashid, for such a wonderful presentation. So it's a time for question and answer session. So if you have any question, you can ask directly or either write in the chat box. So Azha raised her hand. So Azha, you can ask the question.
Okay, as you mentioned about one of your work, facial expression recognition. So what were like the biggest challenges in making facial expression recognition model work accurately, across different ethnicities and lighting conditions and camera qualities?
Yeah, that's a really, really good question. Getting the clean data is, I would say, a challenge. So the biggest challenge is having the nice, good annotation, good quality data, and of course we are aware of the problem, like different camera model, and their image acquisition techniques are different. There are different noises as well, and then there is also some of the issues regarding to generalizability. Yeah, because in different ethnic group they have different facial expression. So we are aware of that. The images that we have used for our research, it's already based on some well-established data. Here you can see these are actually well-known data, and these are very, very clean, so we don't have that problem. But we have a future research direction related to how we can actually use this model for other ethnic group as well. Yeah, because it's a domain adaptation problem. So we are trying to investigate how this can be translated to solve other problems as well. Yeah.
Thank you, Nashid. So can you access the chat box? So there is a question from one of our PhD student.
You want me to 1 minute? Chat box. So I can't see the chat. Okay.
Okay, this one, yes.
Yes. Good.
Thank you.
Stop 5 minutes. When you get 98% accuracy with AML method for classification with intrinsic interpretability, why go for a deep learning model, which is a black box in nature, and also computationally expensive in general? So if you can hit a sparrow with it, oh, right, yes. Because we, so it's a good question, very good question, because we already hit 98% accuracy. But the reason we want to do deep neural network for this model, because we want to investigate, because we want to test. Like we know, like deep neural network is data hungry, and normally what happens, deep neural network beats those conventional machine learning. But when we are doing science and when we are doing research, we need to test it, and we need to back up what we're claiming with our experiment and with our results. So this was one of the reasons, because when you talk with other people, when you back up your claim with evidence, that's more legit, rather than just saying deep learning model will work or will not work, it's explainable, it's not explainable. You need to tell it's explainable, why it's explainable, and how you converse those explainability. Or sometimes the model will give you good accuracy, but you need to then link it with clinical interpretation. And if you say, all right, we're using conventional machine learning and it's giving 98% already, and that's why we're not using deep learning, because we're already getting a good result. But then how you actually back up if you don't run those experiments. So this is one of the research motivation from us. When we run those experiments, we have those matrices, we back up our claim, and that's how we talk to the reviewers, that's how we talk to the clinicians. Yeah? Okay, thanks, Amjad.
Okay, anyone else from the audience?
Yasir, Imran, I guess. Okay, I really enjoyed it. I have a question throughout your presentation. You show the evaluation from handcrafted features and okay, linked list presentation to multi-scale model, which approach contributed the most improving final. So I think you mainly you might be missed it. So the most so here I think. So when you use graph topology features with feature selection, you get the highest score, which is around 98%. Yeah. So when you have 3D graph topological features with the feature selection techniques, you get the highest classification performance. Yeah, improve final classification performance. Yeah.
Okay, thank you so much, Dr. Nashid. Anyone else from the audience? Okay, so thank you so much, Dr. Nashid. I personally enjoyed the presentation a lot, and I hope that your talk has been very beneficial for the students also, especially for those students who are already doing research in this field. So thank you so much to all the audience, to EMS society members, Azza and Yasir, for arranging this presentation for us, for this session for us. So thank you so much, Dr. Nashid, once again.
Yeah, thank you. Thank you for having me and giving me the opportunity to present my work. And I'm always open for discussion and collaboration opportunities. You can see my email here, so feel free to drop me a line if you have a full idea or want to discuss, or if you want to work with us.
Okay, thank you so much. So from audience, if anyone wants to contact Dr. Nashid, here is the email address on the screen. So you can just email her and she will provide you feedback. So thank you so much, Dr. Nashid, once again. Yeah. So with that, I would like to conclude today's session. Thank you all thank you all of you.
All right.
Allah Hafiz.
Everybody, take care. Allah Hafiz.
Bye bye. Allah Hafiz.